Okay, well, thanks again for inviting me and thank you for great introduction. As you know, we've been in contact and discussions with AISweden the past couple of months, and that was really great. And I hope that we will have more actual collaborations from now on. I'll mention as well the context in which it started happening and the neural scaling laws workshops that we were running last fall and winter, and hope to continue running as a part of kind of ever-increasing international collaboration, not just between Mila and AISweden, but also organizations like EleutherAI, LAION in Germany, LAION in France, and well, Hugging Face as well, and perhaps many more as people are joining. I'll talk about that and the plans for that at the end of this presentation. Okay, so let me just give you kind of an overview of some kind of recent developments in the field of scaling laws and foundation models. But even before that, I'd like to pose the problem and question that was driving many of us in various directions, not just scaling. Scaling seems to be one of the potential ways of addressing that question. So I kind of just wanted to start with a classical kind of statement that pretty much many talks, I guess, start these days, but that's still the problem. So as we know, despite the really impressive advances of artificial intelligence in specific domains, which may be extremely complex, like playing Go or chess and detecting abnormalities in X-rays, and even kind of generating paintings that can be really sold at auctions along with human paintings, and then having, of course, the famous GPT-3, which keeps being improved, and the recent Instruct GPT seemed to be even better version of that, as you probably read already. It's definitely all great, and superhuman performance in specific tasks is amazing. Yet we're still striving to get to the holy grail of AI field, essentially general intelligence, instead of narrow and task specific and wonderful. We want agent or a population of agents, just like intelligence that kind of emerged in the natural world. It never emerged in isolation. So perhaps artificial intelligence should also emerge as population. But the distinctive kind of property of that is that we might not be the world best Go players, and my paintings might not be necessarily sold at auctions in New York City, but I can still learn how to draw, how to paint. I can even learn French a little bit, though I just moved from New York 2 years ago. And I can keep learning to some extent a wide variety of tasks. So this ability of human mind to continue learning and be extremely versatile in terms of modalities and types of tasks it can do without necessarily immediately forgetting what I learned before. Well, I never forget how to ride bicycle, though I learned it when I was like, I think 4. So this ability is not quite yet captured by modern artificial intelligence. That's why kind of the holy grail of the field, and many agree, those who dare to call it artificial general intelligence or AGI, essentially that is a goal: broad, general, versatile. Also, there are multiple other important issues that modern AI systems still kind of suffer from. And those issues are very important also for AI safety and for usability of powerful AI systems. And such thing as robustness. This is highly important, because imagine if your system can be perturbed by a little bit of adversarial noise so that human does not even notice and keeps classifying image correctly, and the system is completely destroyed by this little amount of noise and starts misclassifying things. You cannot use such system in any critical application, whether it's autonomous driving or robots acting in the real world or medical diagnosis, right? And we all know about this field of adversarial robustness. I'll mention a few more things about that later. And robustness doesn't necessarily only relates to robustness to adversarial attacks. it can be simply changes in the environment, which for some reasons are not accounted for by the model. And those changes apparently can break the system really kind of significantly. Again, so those examples come from various classical papers from several years ago. And this is a famous cow on the beach example many of you probably have seen. The idea is that if during training, you have certain distribution of your data, and you're trying, for example, classify animals, and you mainly see cows on the green grass, while during the test, you are showing cows on the beach, for example, the data are out of distribution. And unfortunately, again, it was a very nice paper surveying those failure modes. Deep networks have this tendency to fall for easy features, to essentially shortcuts, such as, well, looking at the color of the grass, easy, and you can classify cow versus camel, but unfortunately, it doesn't generalize out of distribution. So the goal of this whole field of kind of distributional robustness, or robustness to distribution shifts, generalizing out of distribution, is to be able to learn models that are invariant or robust to such changes that essentially relate to changes in spuriously correlated features instead of the true invariant kind of descriptions of the animal, such as shape. And this whole field is extremely kind of fast growing, also very interesting, and I think very relevant to the whole scaling large model kind of field, because it relates to the core property of such system, robustness. So just briefly, I kind of wanted to mention again, with adversarial attacks, there are multiple examples. The whole field is kind of flourishing, and this is a classical example of adding a little bit of kind of noise that looks practically random, but is kind of constructed adversarially so that the system will be fooled into misclassifying panda into gibbon or who knows what with extremely high confidence. There are multiple approaches in this whole kind of field, as I mentioned, and we're also kind of quite interested in working on a few approaches. So recently, I mean, this was archive paper earlier, but currently we have this new RIPS paper from last year talking about adversarial feature desensitization. Essentially, it's one type of the approaches which turn out to be actually quite successful, where you focus not just on making the final predictor robust, but rather you focus on making representations robust. In a sense, you just add, for example, adversarial kind of head to your model, and essentially you train not just classifier, but you also try to come up with representations or embeddings so that it's impossible to distinguish representation of the true image from the representation of the adversarially perturbed image. In that sense, the features, extracted features, become not sensitive to attacks. We'll not go into details. You can find everything online on archive or on the basically on the Google Scholar. But the point was that indeed focusing on robustness of features instead of robustness of the final classification task, as many previous kind of approaches used to do, gives you a considerable advantage in terms of robustness, not just to specific attacks, but to different strengths of those attacks. And here is an example of PGD attack on several data sets where the green line corresponds to method that we propose, and the other lines are kind of previously proposed methods. And you can see that the accuracy stays high for much stronger kind of attacks. The strength of the attack is on the x-axis, and it's definitely is much more robust to increasing kind of strengths of attack, and actually it's robust to wider range of attacks. So the lesson here is, if you make representations stable, then it doesn't matter what task you're going to do on top of them, that should help. And another example, as I mentioned, is robustness with respect to distributional shifts, the classical proverbial cows versus camels. And in this line, there are lots of work done on top of the so-called invariant risk minimization approach. Many of you probably also heard about. It was a paper that made quite a splash, appeared in summer 2019 from Facebook, Martin Arjowski, Leon Batu, and collaborators. And in our group, Kartik Ahuja, who is currently a postdoc with me and Joshua and Ioannis Redkakis, he actually developed improved version of IRM called IRM Games, and then further build on top of that. I will not have much time to go into all the details. It's also a bit of a dense topic, but the idea of IRM, just as idea of many methods that are built on top of that, is that you try to build model that will be robust simultaneously across a wide range of environmental data sets. And the distinguishing feature of the robust or invariant versus spuriously correlated features is that even though spuriously correlated may be correlated highly, the correlation level varies, while the true features, even they are maybe correlated slightly less with a class, that correlation remains stable. Anyway, I don't have much time to describe everything, but the principle is, let's give the model multiple data sets that share something in common, such as, well, cows or animals and their kind of features, and, for example, vary in terms of backgrounds. Could be, of course, other examples. And the point is that you're trying to learn simultaneously representation phi and classifier on top of that, so that the classifier can be simultaneously optimal across all the environments. And essentially it means that if you manage to find such a mapping into such features, they are robust, and that space, essentially all the perturbations in the data do not matter, and the classifier is simultaneously optimal. Again, this is kind of a separate, it's worth a separate presentation, probably even a few hours. And if you didn't read the IRM paper, I encourage you to look into that. But it has various failure modes. And again, last year, there were several papers exploring those failure modes, including ours, which came out at New Rips as well, where Kartik and collaborators actually explored a few cases when IRM doesn't work and how to improve it. And it turned out that adding extra regularization to the IRM problem formulation that's based on information bottleneck can kind of basically alleviate those issues. It can fix a few kind of holes in IRM. Well, of course, nothing is perfect and there is still room for improvement, but I think it's important to keep first understanding better when robustness imposing methods are supposed to work and when they're not supposed to work, because you will have all kind of different types of distribution shifts, and also providing methods that are, again, even more robust across different types of such distribution shifts. There was another line of work also from our group on top of another very nice method related to invariant representation learning called invariant learning consistency, actually from the Max Planck Institute, from Bernard Scholkop's group, by Giambattista and his collaborators. Again, don't have much time, but just want to say that the principle here and observation was quite kind of related to the previous one. Essentially, it was saying that if you have multiple environments, like say this toy example, and you can have multiple good solutions or good models here looking like local minima, it's important to search for the solution or local minimum or actually model that will be simultaneously good across multiple environments. And the point is that if you compute average loss across multiple environments, those kind of this information may disappear. You cannot anymore take kind of intersection or look for something like stability, because everything will be clumped together in one average loss. And that's not a good idea. So that paper kind of advocates looking at those samples in the mini batch or environments or subsets separately and trying to align gradients so that essentially you only make steps in the directions on which most of those samples or different environments agree. And that was so-called end mask for the gradient. And actually it was quite promising. It was beating IRM in some data sets, but not all. However, it has some other issues, and that involved, for example, again, technical thing, but it involved kind of getting into flat regions in the search space where gradients would be just zero and you couldn't move because of that mask. And we had to kind of see how we can avoid this issue by introducing somewhat smoother version of that end mask to avoid those dead zones. Again, the paper is out there, everything is online, and the result was on this famous benchmark, the main bed, which we, by the way, keep extending, and Kartik and Jean-Christophe, also student in my group, work on adding more and more state-of-art methods and various data sets to the benchmark. So it's kind of really nice to test new methods on. This smoothed mask was indeed providing better results, for example, colored mist. Of course, it was not ideal, but I'm just giving examples of different efforts towards improving robustness methods in kind of different settings. And just to kind of give you this final overview of what else you can do with robustness, it's not just in a classical setting of single data set and single kind of training and test. It's also quite applicable in the distributed learning setting. For example, in federated learning, imagine you have medical data sets which you cannot really share across different hospitals for privacy reasons. And in general, any kind of applications where data sets cannot be possibly shared in central location may have a similar kind of flavor. And the question is, how do you learn joint model given such constraints? So that's a whole field of federated learning. And apparently, you also can ask the same question, how you learn a model that is also robust to considerable shifts in the data distribution. That was a work with Irene Tennyson, who is one of the students in our group, and also Shreya Francis. It was a workshop paper, it's still work in progress. But essentially the result was that if you impose this invariant learning consistency type of kind of constraints on your learning and this mask on gradients, you do end up learning a joint model that will be better performing than model learned by kind of classical federated learning approaches. And finally, one of the big themes in our group is continual learning, as you might know. And indeed, if you think about learning in any realistic environment, most of the time, like applications such as robotics or self-driving cars, or even conversational agents, the application, I mean, the setting is somewhat non-stationary, and the tasks change and the properties of environment change. The same person may be doing different things during the day, and if the smart assistant is supposed to be helpful, it has to be able to switch to new kind of tasks and activities. And also it has to be able to adapt to changes in the data distribution. And even more, if you want conversational agent that can be more general and learn sequentially from different users, instead of like re-implementing a new conversational agent, for example, for new organization. That's a problem that occurred many times back at IBM Research when I was there. And that was always kind of a concern that for each new customer, you have to develop new conversational agent instead of somehow transferring knowledge or continually learning across kind of different customers. So this problem pops up everywhere, and the problem eventually is to kind of mimic that human ability of learning sequentially from different data to do different things, and not really forgetting completely what you just learned before when you kind of retraining on the new task. And it's still a good open question with large scale models, whether training them the way they're trained right now, which means with a large data set and kind of shuffled data with one large model from the beginning, is the best way, or perhaps learning them continually in incremental way and imposing this property of adapting without forgetting using continual learning algorithms. Maybe this approach can also yield more robust large-scale models. So it remains to be explored. Anyway, so I'm just kind of giving the very high-level gist of continual learning and what the problem looks like. Basically, it's online and it's non-stationary, since your data samples keep coming from different data sets or data distributions or tasks. Locally, the data can be IID because they're coming from same data set, but those data sets kind of keep coming your way. And you want to learn a model, just like with large-scale model setting, that is capable of either remembering everything or being able to be a good few-shot learner, like quick remembering instead of completely not forgetting. Anyway, so that's a field, large field with a separate, like large history, starting from computational neuroscience and all the way to modern days, and the huge spike in continual learning kind of literature in the past, essentially past decade. Everything started growing exponentially in deep learning since 2012 and AlexNet moment. And now, interestingly, there are kind of observations that perhaps the GPT-3 success may be another AlexNet moment, but for the field called, well, AI alignment or safety, because now the models are capable of doing things they were not capable of doing before, and alignment and safety become much more of a real issue. But back to continual learning, as I said, it's non-stationary, online, and that's different from the standard classical learning with training data and test data, and you're done. And the issue is that since you don't have always access to all the data, to optimize expected loss across all tasks, you need some ways of remembering the past, whether explicitly with replay-based methods or through adding some regularizers to your basically learning algorithm, or in some way trying to compress and remember all the previous tasks from your history, at least to the point that you can quickly remember from few samples later on. And if you don't do anything smart about that and simply train SGD-like algorithms kind of sequentially, you get this classical catastrophic forgetting phenomenon, as many of you probably know. Essentially, training on new tasks makes you perform worse and worse on previous tasks. And the whole problem in the field is essentially not just to solve that catastrophic forgetting, which is often kind of claimed to be equal to the goal of continual learning. It's a bit more general goal, and the large-scale models can really help here. I'll talk about that later. And the goal is, since you have weight sharing across kind of, it's the same model, you share weights across different tasks, essentially. You want to be able to learn those weights so that there is a transfer. Transfer both to the past and to the future. And essentially, kind of any way of making your weights aligned with a wide variety of data sets is something that we want. And just like to give some examples of what can happen, it's from nice tutorial from last year, actually from 2020. The failure modes in continual learning may include the forgetting. Learning new tasks makes you forget the previous. But you also may have other issues like lack of plasticity. You learn well the first task and then you cannot really adapt. And ideally, you want to have the stability and plasticity. And even better, you want to have the positive transfer both in future and the past. Every time you learn a task, your performance even improves on the previous and hopefully future tasks. So that's kind of the roadmap for continual learning. And just kind of one classical approach to that, just give you a hint, but I don't have much time to go into all details. You can look again. And this particular paper, there are basically lots of other papers before and after that that use the same principle. But one of the common principles to align the weights with the previous and kind of current and future tasks is to make sure that basically gradients computed on, say, current sample are looking in the same direction, more or less, as gradients on the samples from the past. And if you just take the dot product of the gradients, and if it's non-negative, essentially taking step from the current sample in the direction of gradient will somewhat help, or at least not hurt, the performance on the other sample. But if the gradients look in the opposite directions, unfortunately, that's where interference or forgetting may happen. So that principle that you can incorporate in various flavors of continual learning algorithms. Anyway, so there is a long list of properties we want from such systems. You definitely need some constant memory because a stream of tasks can be infinite. You may not even be told when tasks change. You have no task boundary. You're learning online. You want forward and backward transfer. Forward transfer is essentially what people also call out of distribution generalization. And if you also allow few short learning, that's exactly what large scale systems like GPT-3 are good at, that forward transfer, but you also want backward transfer. That's not exactly something explicitly talked about in context of those systems, but in continual setting, that becomes important. So on and so forth, and without, again, kind of not having too much time left, but without going into too many details, the issue is there are many different settings and particular formulations for continual learning problem in terms of how the data change and how the task change. So there are also extension to continual meta continual, and other flavors of hybrid type of continual learning. So we kind of tried to unify those in this, well, back in 2020, new RIPS paper, to unify them in one kind of setting, which would be including all of those, and try to come up with method that could handle such a setting. It was called continual MAML, as a continual version of the famous meta-learning algorithm. And essentially, okay, skipping that example, essentially it was a formulation that encompassed and included all the others without too many details. What I just want to say that, yes, we tried it on a variety of classical benchmarks, mainly imaging benchmarks, because continual learning these days is still mainly focused on like CIFAR100, well, hopefully not anymore on permuted and rotated MNIST, but like Omniglot and all other type of imaging data sets, which, by the way, is a very interesting and underexplored kind of niche to look at the continual learning in the natural language domain. There is work there, but not nearly as much as with images. And perhaps I keep thinking that perhaps trying to train systems like GPT-3 in a continual learning manner with some successful continual learning algorithms may perhaps yield even better models than the training that is being done right now. It remains to be explored, and if anyone wants to kind of explore it together with us, I would be very happy to discuss. But back to this kind of framework, yes, indeed, it showed that not only it's more general, but the approach can keep remembering previous tasks when the competitors could not, when changing from like Omniglot to MNIST to Fashion MNIST and in different other combinations. Okay, to kind of conclude with the continual learning detour and get back to scaling, for which we have less than 30 minutes left, just wanted to say that besides these examples of supervised continual learning, a classical example, as well as unsupervised continual learning that I didn't talk about yet, more about that is in our last summer ICML tutorial with Vincenzo Monaca. He focused on unsupervised continual learning. Reinforcement learning in continual setting is the most challenging and also interesting domain. So we have this survey on continual reinforcement learning, which is also online, which talks about not just different approaches, but different benchmarks and different evaluation criteria, and tries to give the taxonomy of all that to overview the field. But since the moment it was written, I'm pretty sure there are many more methods developed in the field. But it's I think the most exciting and the ultimate continual learning setting where you truly have an agent that acts in the world, whether real or virtual. And tool-wise, on the software side, we developed this system. Primarily, it was one of the students in my group, Fabrice Normandin, and well, also with Massimo, who kind of co-supervised him, but they developed a really nice system that encompasses multiple formulations for continual learning, including reinforcement learning and so on. provides a common set of benchmarks and evaluation criteria. It was used very nicely for the CVPR competition and continual learning. Hopefully we'll use it again, because it's very easy for researchers to plug in their methods and just have all the evaluation all the evaluation code already there without the need to re-implement it. So anyway, if you're interested, you're welcome to ask me, or it's all open source on GitHub. Okay, so to conclude with continual learning story and where it kind of goes to scaling finally, one view at the role or the kind of purpose of continual learning could be to come up, just like evolution came up with our brains, a large network. So scaling is, of course, important part, but only a part of that. So you do scale, but the question is, how do you scale, and in response to what? So you can imagine that if scaling of models or growing a brain is done in continual fashion, then what you want in the end, as I was saying, is a general intelligence that can solve a wide variety of possible tasks in wide variety of environments, switching from one to another. Our brains are at least existing examples that that's possible. And there are also existing examples that scaling managed to achieve such result. So whenever there are arguments on Twitter or otherwise that scaling can never lead to general intelligence because we just cannot make the models understand, or those models just cannot, I don't know, have reasoning and so on and so forth, the answer is they might not be yet that good at that. But first of all, there are clear improvements, but ultimately you do have one positive sample when scaling of a network did lead to what we call, well, general intelligence, or at least as general as it gets among humans. So it's not impossible. Of course, the question is how you scale, what type of architectures you scale, what are the constraints, and most importantly, what is the environment? Because environment is really crucial. Environment means data sets that you expose your system to, because essentially it has to be sufficiently diverse and complex. And there are many studies, of course, in neuroscience, what happens with development of, say, rats who are not in the rich challenging environment. They, of course, do not develop as well, and well, humans too. So it's important to have proper environment to grow to scale your kind of artificial network as well. And this kind of schematic slide that I usually like to show is basically supposed to convey the following message. If you think about, say, supervised continual learning, each time you see a new task, you have to learn a function. Neural net is, after all, just a function approximator. Well, talking in supervised setting, we can kind of transfer it to other settings as well. And you learn the function for one data set and type of functions, then you have to switch to new ones. You have to learn an infinite sequence of such functions. But if the world or the set of all possible data sets and environment in the future is structured in a sense that there exists some finite set of those basic components, so basically some independent orthogonal quote unquote type of components or mechanisms, if we're talking about functions, along the lines of Yoshua Bengio's work on basically in recurrent independent mechanism and other type of papers. If there is this finite set that, if recombined, can solve any task or represent any data downstream, then it should be possible to represent and learn those components in a network and a way of combining them, just like essentially the brain developed to have certain components or kind of quote unquote orthogonal or independent mechanisms for different things, such as perception of visual perception, auditory, motor control, and you name it. So different areas of brains kind of focusing on different functional components. So it should not be completely impossible to go along those lines and perhaps build the finite set of functional components that comprise a network, and recombined, they can eventually solve any task that comes your way later on. And you can think about the newborn brain probably as a pre-trained network during evolution that already managed to kind of extract those main components, and all you need to do is some fine-tuning. Well, it's a lot of fine-tuning, to be honest, but still, it was well pre-trained during evolution process. And finally, in the remaining, 20 minutes, I'm getting to the foundation models and the whole scaling issue. So this goal, this motivation to be able to create systems that are broad, general, right? That was a challenge that can be approached in different ways. And with continual learning or without, but the recent successes of very large scale models that were pre-trained on rich, diverse, large-scale data sets seem to show us, like we know about GPT-3, that generalization out of distribution, or the few-shot kind of adaptation to broad range of novel tasks, is indeed significantly improved. So we're really making steps towards the goal of general intelligence, even though, of course, we are not there yet, and that's why the Twitter criticism is clearly understood, but you should take things kind of with a grain of salt. We are still training the brain of yet unborn AGI infant. So be patient, people. Okay. So anyway, with foundation models like Stanford, actually Center for Research on Foundation Models called them in that paper, they call them foundation models because essentially, on one hand, they're popping up in different modalities, GPT-3 for language and other kind of competing systems, Clip and DALL-E for image and text. And there are more and more system people actually working on acoustic signals, on various multimodal models. They, in a sense, serve as a basis for future kind of more capable models, both in research and in industry. There are many GPT-3 powered startups, we all know about that, and there will be more and more. And that's why the point was that those foundation models indeed provide the basis on top of which research and applications will be happening. But at the same time, they're foundational because they are incomplete. They are not, they're somewhat raw. You cannot just take their output and immediately use it in applications downstream. You may need to add something on top of that. Classical examples, of course, GPT-3 had that unfortunate situation with suggesting the kind of not a real patient, but kind of the simulated patient complaining about depression and asking whether like he needs to kill himself, and the system replying, yes, I think you should, and many other examples of undesirable output of GPT-3. Well, of course, you need to take it with a grain of salt, and it's unfinished yet foundation. And that's why the whole Stanford Research Center was formed and the paper was written that now is a good time to focus on how should we go about building those models in a better way, and what should we do on top of them, and what kind of potential issues and risks we should consider. So it's really a good way because we can influence creation of those models and their properties. And as I keep saying, it might be much easier to train properly a large-scale model and provide sequences of data that steer it towards a desirable behavior, just like you may not want to actually give a 5-year-old unrestricted access to all of YouTube on the internet, and you provide at least some limited supervision. And after learning perhaps which data to learn from and which data to skip, the system may be steered towards a better behavior. Or of course, you can learn in completely unrestricted way. And instead of like proper parenting, you may need to do lots of psychotherapy on top of the adult GPT-3. And as you can see, it can be actually quite successful. Instruct GPT did just that. You applied reinforcement learning to retrain GPT-3 to behave more properly. But I think in a sense, proper parenting combined with adult psychotherapy cannot hurt. And that applies to large scale models. But in any case, I mean, all these examples you know about CLIP in May 2020, I mean, the GPT-3 CLIP and DALL-E were actually January last year. Then Copilot, essentially writing, I don't know, according to people, from 20 to 50% of code being like completed and written jointly with a human, and the list goes on. It's just like a few recent impressive examples. So you see where it's all, it's definitely kind of the progress is definitely fast. And again, I don't probably even have to repeat all that, but as many of you know, that GPT-3, the language model, essentially learning to represent the conditional probability of future tokens, future words given the past, with particularly kind of neat attention-based transformer approach, which allows you to grasp long-term, long kind of distance relationship across words much better than previous methods. That perhaps helps to make those models able to produce much more coherent text, because this long-range dependencies that are caught by attention is something that really needed to kind of generate truly coherent text. And the previous versions had probably that type of long-range coherency in much smaller scale. Like that perhaps could be one of the key advantages of using transformers here. But size-wise, yeah, the thing was kind of orders of magnitude larger than predecessors, all of them, not just GPT-2. We know that it had 175 billion parameters and 45 terabytes of training data, which is important. As I was saying, I think the properties of training data are, of course, extremely important for the capabilities of the model, and it's still underexplored area of studying not just the size of pre-training data set, but complexity and diversity. Just like with rats in rich or poor environments, and with kids watching particular parts of YouTube videos versus other parts, data matter. And yeah, as we know, there was a whole set of GPT-3, the family of GPT-3 models, which is nice because you can study the scaling behavior when you have like sequence of those checkpoints from smaller to larger. And there are also, as we know, publicly available models that try to kind of reconstruct behavior of GPT-3, EleutherAI, and others at smaller scales, but nevertheless quite competitive with respect to similar scale models from OpenAI. And the data set was indeed immense and combined these books, basically several books, data sets from whatever they could find in pretty much all of the internet and Wikipedia and so on. So again, the diversity and complexity of pre-training data is quite important, but perhaps it's also important to add certain type of initial maybe supervision. I'm just like thinking aloud here, to maybe teach the system that whenever it sees kind of interesting book, it should definitely read it. If it sees some racial slur on Twitter, maybe it should skip it and not necessarily learn statistical dependencies and predicting probability of this type of kind of output. It's debatable because you also need to know what is appropriate and what is not appropriate. And the only way to learn it is to see this inappropriate and so-called bad type of output. But perhaps you need to see it when you already have some notion, some classifier that's pre-trained to judge whether what you see is good or bad. It remains to be open question, whether you built it into training or you add it later on top of statistical systems such as GPT-3 that have seen everything. Anyway, so I'm probably going to skip details. You all know how it works, and that the claim to fame is few-shot learning. That indeed, step closer to general intelligence is that you do not know any of those tasks when you train the system. You just do it in an unsupervised way. And because it managed to capture very, I think, core statistical properties of language, because it was exposed to such a diverse data in such a large amount, and its very large model So it has capacity to incorporate this kind of patterns. Now, anything comes its way, language-wise, or more generally, even like arithmetic-wise or coding-wise, and you can adapt it. It's enough just to see a few examples of that. So that's kind of generalization is something that continual learning I was talking about earlier was trying to get at. Out of distribution generalization with all invariant robust predictors try to get at. And maybe one quite promising way of getting at that is proper scaling of the model with proper scaling of the data, where proper is an open research question. Anyway, so that's kind of the famous plot from GPT-3 paper showing that increase in scale does considerably increase a few shot learning performance. So like, no doubt about that. And why it's important for machine learning field in general, not just for natural language, not just for kind of general intelligence eventually, it's really even just important for pretty much any machine learning paper that proposes a novel approach or novel algorithm or novel architecture. It's important to switch from our traditional comparisons in terms of kind of points in performance to curves. Like usually what do? We have a benchmark of fixed size, and we have architecture of fixed size, and we say, oh, my algorithm beats your algorithm on this architecture, on this benchmark. So you basically have a point in the table. Instead, if you look at the scaling plot and you say, well, my algorithm, if you were to increase your model size, which you hopefully will be able to do with increasing the compute in the future, and you could scale the data similarly, how the curve of my approach would compare to the curve of yours, it might well happen just like with convnets versus vision transformers, that convnets traditionally were kind of the state of art in image processing, and they're really good when the data are relatively small, again, relatively 10 million, right, samples, small. But apparently the situation reverses when the data become really large at 100 million and transformers start to take over. And there is no way you can see this trend unless you do some scaling plots. And you don't have to have humongous compute to do scaling plots. It's a common misconception in the field. Pretty much every time people hear for the first time about scaling, they say, but we don't have large compute. And I say, and you don't have to. You can do scaling studies with what you have right now. Just you need to plot curves instead of tables with points, because you may be able to extrapolate. And that's a whole beauty of scaling laws, as we know, that you can be able to extrapolate and see which method in the future may be advantageous. So, okay, I will probably skip all these cute examples of the multimodal systems. You've seen that probably many times about CLIP that kind of zero shot outperforms state-of-art model on data sets which are essentially out of distribution, while the model that was kind of trained on the ImageNet is really kind of good at ImageNet. CLIP kind of matches that performance, but out of distribution, that model just cannot do anything. And CLIP, as it was pre-trained on the diverse and wide range of data sets with sufficient size of the model and incorporated those dependencies, it works quite well on this out of distribution data, like now pictures of sketches and so on, something that the other system totally fails miserably and doesn't generalize out of distribution. And then DALL-E does the opposite. You describe what you want, like this photo of cat, and you want the sketch of it, and it does it, and it's pretty mind-boggling. And when it just came out a year ago, it was like truly, truly impressive, and it's still impressive. And since then, there are also kind of more improvements in terms of how to generate images just based on text, and in general, how to expand models to handle different modalities and not just images and text, perhaps acoustic, perhaps other, like you can think about possibly even expanding it to graph data and possibly even applying to drug design. You can represent the molecules and graphs, and you can think about time series for, say, brain imaging data. And then there are all kind of other interesting questions: to what extent your feature extraction or representation learning core part of the model, to what extent it's transferable across different modalities, to what extent it's transferable across different applications. Can you train on brain data and then work well on finance, or train on finance and work well on multivariate time series for weather prediction, or even train on semi-simulated data in infinite amounts of those time series, for example, I know, random subsets of Fourier spectrum, pre-train and see whether it helps you to perform better on particular application. There are some promising kind of indications that, for example, pre-training on YouTube, just relatively small part of that with relatively small model, can already improve your performance on, for example, functional MRI time series. You only can wonder what happens if you scale both the pre-training data and the model. Yeah, so it's kind of seem to be very promising. In any case, so examples go on, and I'll probably will have to really speed up within 5 minutes left. What I wanted to say also about the study of large-scale models, it kind of goes back to this whole philosophy that was kind of always present, at least in part of the AI community, about treating our models and algorithms and our empirical evaluation of them as empirical science. Essentially, the fact that you have created some large-scale complex system that might be now even difficult to understand in full detail, like deep networks, extremely large, trained on extremely large data, you might not be able to understand them at the detailed approach. But same goes about statistical mechanics, right? You have very large-scale system, and at that scale, you can view regularities and behavior of the system as whole, depending on certain like properties of the underlying like network of interaction among the particles. You can look in similar ways at behavior of large AI systems, and you can study that with respect to certain variables that you think are important. So essentially, we're kind of doing thermodynamics of AI, where instead of temperature and pressure, we might be kind of looking at some properties of data or properties of model and trying to link statistical mechanics with thermodynamics there. Anyways, the line of thought was out there. I kind of was very interested in that as well, even back in 2000, and had this workshop paper trying to make precisely the same point, that the fact that systems are artificial doesn't matter. We can study them just like natural, because at some point there are common properties of all complex systems. And it would be good to understand which properties are in common with, say, biological networks, with neural networks in brain, with physical systems, and what properties are different. It's going along the lines of this analogy that in order to fly, the airplane doesn't have to flap its wings like the bird does, but both the bird flight and airplane flight, they both follow the laws of aerodynamics. So we need to build aerodynamics of intelligence. Yeah, well, kind of easy problem, can be given as a project for the scaling laws class this semester. Anyway, so I'm running out of time. Just wanted to give a few examples that this empirical analysis of regularities and behavior of AI algorithms has indeed long and broad history. For example, studying phase transitions in constraint satisfaction problems and resatisfiability was quite an active area of research. And it has very interesting analogies with spin glasses and the reason for transition to happen. There are similar kind of approaches to studying random graphs. It's a whole interesting area. But again, it's all about large-scale system of interacting components. And when properties of that network density and way of interaction kind of change, so that the global behavior such as satisfiability versus lack of it may change. If say number of constraints starts increasing from 0 to everything being a constrained system may go very rapidly from having probability 1 of being satisfiable to probability 1 of being not, and transition is sharper and sharper as the size of the system increases. So at scale, you start seeing those laws in action. Anyway, so the story goes on, and I'm really happy, and many of us happy to see that companies like Anthropic state precisely as a goal, as one of the goals of the company, studying AI as complex natural, well, artificial systems, and using like systematic science in order to understand how neural networks behave, because with this understanding, you can predict their behavior and you can choose approaches that will let you build better systems. And that's really kind of making AI science empirical instead of completely engineering field. Anyway, so in terms of scaling laws, maybe I'll just try to wrap up in a few minutes. You probably all have seen the GPT-3 paper, famous plot, essentially showing you that particular type of scaling law that made people excited was this very kind of simple power law, the line in log-log plot, which relates the loss on the test data with compute power, and similar plots also apparently hold for dependence on data set size and parameters. Again, you've all seen those, the paper by Jared Kaplan and collaborators, and many papers in that line of research on looking into scaling laws in transfer and in continual learning more recently and so on. So the simplicity of that power law is indeed something remarkable, and all you need to do is to evaluate a few parameters, and you'll be able to extrapolate and compare different methods and search for methods, properties of data, and architectures that hopefully have better exponent, that are steeper and give you smaller test laws for smaller kind of cost of compute. So that's kind of the whole point. To keep in mind, actually, it's not just power law. The full picture is more like a sigmoid, but sigmoid-like curve. And it's interesting to also study questions like when it kind of starts tipping into the flat kind of straight line, and at what point the system that doesn't perform well at all suddenly starts improving, and whether it happens like a phase transition or it's very slow. And it depends on data, depends on downstream task, depends on the model, depends on everything. So again, that's an empirical question to explore. So to wrap up, what do we learn from the large-scale model research in the past years? That first of all, the ability to be few-shot learners without fine-tuning, that's the property we always wanted to have in those general AI systems. So it's clearly we're going apparently in the right direction with that by doing scalability kind of studies. And the interesting thing, it's again, I mean, it's just a curious observation, but the fact that apparently there were studies about brain activity during language processing in human brains, and there is some striking similarity between that and the activity on certain hidden layers of GPT-3. If you're interested, you can take a look at that paper from last November. And why it's all important? Well, the neural scaling laws, especially when they're simplistic enough and they capture performance so that you can extrapolate in the future, and the extrapolation is accurate, as it turned out to be the case with GPT-3, you can use it to your advantage because basically scaling laws are your investment tools. They suggest which methods, algorithms, or ways of training you should invest into, so you will survive the test of time and will not have to learn the so-called bitter lesson, as it was put, that essentially the whole history of AI seemed to be going from sophisticated, expert-based type of knowledge encoded, whether it's rule-based systems or any kind of heuristics that are domain-specific, when you don't have enough data or large enough models. They're all kind of thrown away eventually and replaced by more generic approaches like massive search for for example, chess program that beat Kasparov, and self-play at large scale, and essentially like generic deep network learning with AlphaGo, and examples keep coming. Well, now you pretty much threw away most of the domain knowledge, and yet just by scaling generic architecture of a transformer, you get pretty good natural language models. So bitter lesson seem to apply again and again, and we want to now think about what should we do now, so we will not have to learn that lesson again 10 years from now. And of course, nothing is perfect and nothing is completely explored. And there are so many properties of those systems that may behave actually differently from just the kind of upstream test loss or even downstream task performance. Besides performance and classification accuracy and cross entropy loss, you have other desirable properties such as robustness, say to distribution shift, such as truthfulness. And for example, this type of properties in the paper, recent paper on truthful Q&A were shown to exhibit so-called inverse scaling. They actually get worse with increasing training data size, perhaps because the system picks up all kind of garbage in the data as well. And you need to do something either during training or after, like instruct GPT to kind of counteract those undesirable inverse scaling situations. But it's completely open area of research, studying the whole range of desirable properties and their behaviors. But it seems like, indeed, as I said, the bitter lesson is here to stay so far, and we don't want to fall kind of into the same, we don't want to step on the same rake again and again, hopefully. And compute seemed to play a larger role in improving those capabilities. That was a classical plot we've seen about the steep increase in compute power needed to train the most successful recent deep learning systems. To conclude, I just want to say that, yeah, it may be a bit of a kind of bold statement, but I think it has good points to that. Greg Brockman from OpenAI, we think the most benefits will go to whoever has the biggest computer. And if that's the case, as we know, most of the computers owned by companies, by private sector, and they keep building better clusters and supercomputers, like recent news about Facebook and so on. So academia and nonprofit organizations kind of are in a situation where this compute gap continues to widen. So we're trying to figure out what we can do about that. And as you know, there are multiple organizations. Actually, I want to talk about the multiple organizations that are trying to kind of take some steps in that direction and maybe unite their efforts, like LAION and Yuli Center, application for dual supercomputer jointly with collaborators, including us and others. And you guys are looking into the same type of trying to identify common problems in large-scale model learning, try to maybe join forces internationally with other groups, and try to jointly apply for supercomputers. Here is just an example of specifications. So for example, Summit and Frontier, there are multiple supercomputers around the world, but those are kind of pretty large, and trying to apply as a collaboration could give you, well, maybe not the whole 27.6 thousand GPUs at Summit, but at least maybe 50–60% of that, which is pretty good already. And Frontier kind of promises to be much larger with 40,000 GPUs, and so on and so forth. So essentially, I think that could be a plausible way to proceed in this race for compute if we want to stay on top of the kind of cutting edge AI performance, perhaps uniting our efforts with different universities and organizations and trying to jointly ask for compute resources, or perhaps, I mean, try to lobby governments to build larger clusters of supercomputers might be something that we need to do. Okay, So thank you so much. Apologize for running over time. And there are some resources here. The neural scaling laws I'm teaching right now, winter semester at UDM and Mila, everything online. All the materials are posted. Anyone can join, by the way, link is out there. Mondays, Thursdays at 4:30 Eastern time. And the information about our 2 workshops with all the talks and materials also available online. Thank you.
Great, thank you, Irina. That was a really interesting presentation. Lots of useful and condensed material. I would love to extend this to several hours or maybe even days. I mean, there's so much material here. So we don't have any questions in the chat. Do we have any questions from the participants?